Okay. So suppose we wanted to find the equation of a plane in part A, for example, that is passing through 3 points as described there. So what is happening there? First thing is to picture it. Suppose this is such a plane. Let's say those 3 points lie on the plane. Let's say that's one of the points and that's the other. To describe a plane, we need two things. We need a point on the plane. Well, we've got 3 points, so that's sorted out. But the problem is a vector that is perpendicular to the plane. So that is what we need to figure out. A vector perpendicular to the plane. So what we're going to do is we'll pick the point, label this as P, Q, R. So take this as P, Q, and R. So get a displacement vector from P to Q, then P to R. Once we have the two displacement vectors, we take advantage of a cross product because we know if we get a cross product of two vectors which lie on one plane, the product is going to be a vector perpendicular to both vectors, or the product will be a vector perpendicular to the plane. So it doesn't matter the order we cross these. Either the normal will point up or it will point down. But we go with PR cross PQ. So first thing that we do, we get the displacement vectors. PQ or PR. So final is at arrow. So I'll go arrow. I have 4 in the X minus 1 from P. Then from arrow minus 1. From P, I have 2. Then from R, I have 3. From Q, I have minus 4, which becomes plus 4. Now, you don't have to worry about why did I say PR? Why not RP? Why didn't I say QR or QP? It doesn't matter. Just pair them and then stick to whatever you've selected. So this one becomes 3i minus 3j plus 7k. In the same way, let's get PQ. Find out Q. So here I have 237. Initially that P, 1, 2 minus 4. Minus 4 will make this plus 4. So I simplify. I'll have I here plus j here, and then plus 11k here. Let's confirm that one, the last one. So Q came with 7, and 7 minus 4. Okay, giving us that 11. So this is our PQ. Now let's get the cross product. So we saw that a vector perpendicular to what we're looking for will be obtained by the cross product. PR cross PQ. To obtain the cross product, we'll use the determinant method. I, J, N. So from PR, we have 3 minus 3, 7. From PQ, 1, 1, 11. From here, when we get I, we have minus 3 by 11, which is minus 33, minus 1 and 7, 7. When we get J, we'll have 3 and 11, which will be 33, minus, then we'll have 1 and 7, which will still be 7. When we get K, we have 3 and 1, which will be 3, minus 3 and minus 3 and 1, 2 minus 3, making this plus. We've been doing the determinant method for some time, so I've just gone through it a little bit quick. So this would be minus 40i. Then the difference here will be minus, is it 26? You guys can verify this. Is it 26? Is it? I think it is. Okay, so that is what we get. So this becomes our normal vector. So from the normal, remember, this is where we extract A, B, and C. So we're getting A here as minus 40, B minus 26, C, yes?
That's what I suppose is
Use what? Use what? PQ? I said PQ cross PR. The difference should be these are positive for you. They change signs, is it? Yes. So the condition is that you need a vector perpendicular to the plane. Whether the vector points up or down, not perpendicular. If I have a line like this, perpendicular to this line can be up and also be down. So yours points in one direction, mine points in the opposite direction. You get that, right? So it doesn't matter. Okay. So we are now here. So next we have the normal. We need a point on the plane. So pick any point. Since you are given 3, you're rich, we'll get P. 1, 2, minus 4. 1, 2, minus 4. From a point on the plane, we'll get x0, y0, and z0. So this is now what we have. Now, how do we finish this to get the scalar equation? The scalar equation will be A, open bracket, x minus x0 plus B, y minus y0 plus C, z minus z0. This is our scalar equation. We can simplify it a little bit to get what our D is going to be there. But let's make the substitution. Remember, we already have A, B, C. x0, y0, z0. We'll leave x, y, z as variables. So our a minus 40. Our x is a variable. Our x0 is 1. Then plus our b is minus 26. Then we have y minus our y0 is 2. Then plus our c is 6. Then z minus our z0 is minus 4, making this plus 4. You should see here that this is reducing to the same expression that you had. Do you see that?
Yes.
Yeah. So it would to give the same answer as yours. So you have plus here, 52, 6z, then that will be 24. Is equals to 0. So can we arrange? I'll leave the numbers on the left, take the variables on to the right. I have 40 plus 50 plus 30. So 40 and the 52 there, I have 92, 92, 96, 96. And I have 116, is it?
118.
118.
Yes.
No, it's 116.
116, I think.
Yes, 116.
116. So we'll have 40x. I'm taking them to the right, so they will change signs. Plus 26y minus 6z will be equals to 116. They are all even numbers. I can divide by 2. So this is 20x, 13y, 3z, 116. Half of it would be 58. 58. That becomes our scalar equation. Is this what you had? There you have it. Doesn't matter which points you pick, how you pair them, how you cross them, you end up with the same vector equation. Any questions? Let's look at B here now. In B, now they're saying they want the equation for a plane, and this plane, what do we have here? So this plane is perpendicular to the line. So it is perpendicular to the line, so they're describing the line here. X is equals to 2t, y is equal to 2 minus t, and z is equals to minus 1 plus t, and intersects L at a point. So we'll be given a point of intersection. Two, 1, 0. So just understand what I'm saying here. We're finding an equation of a plane, and this plane is perpendicular to the line. So it is perpendicular to the line, and it intersects that line at that point. So let's try to understand being perpendicular to a line. What can we learn from that? You see, since our plane is perpendicular to the given line, it means that that given line must tell us something. But the question is, what can it tell us? So if this was our plane, it is perpendicular to another line. It means that that line comes like that. What do we see? You see, since we're given the line, the expression for the line, we can easily determine the vector that points in the direction of the line. What we're given are parametric equations of the line. In vector form, this line would be x, y, z. A point on the line. From here, we get 0. From here, we get 2. Here, we get -1. Parameter here we're using is t. And then from here, we get 2. From here, we get -1. Here, we get +1. So this part here is the part that points in the direction of the line. This is a vector in the direction of the line. And guess what? Since this line is perpendicular to our plane, it means that any vector that points in the direction of the line is perpendicular to the plane as well. So that vector which is in the direction of the line, since the line is perpendicular to the plane, this vector is perpendicular to the plane, this vector will act as our normal. 2i, j, and k. So this was actually straightforward. So already we have our a is 2, our b is -1, our c is 1. Now next thing, we need a point on the plane. Well, it was straightforward. They say the line and the plane intersect at this point. What does that mean? This point is on the line and it is also on the plane. So this point is practically this point here. It's a point on the plane. It qualifies. So the point on the plane becomes that same 2, 1, 0. From here, we get x0, y0, and z0. There we have it. Had very little to do here. X minus x0, b, y minus y0, c, z minus z0. Our a is 2. Our x0 is 2. Our b is -1, making this sign a minus on the middle. Our y0 is 1. Then our c is 1. And our z0 is 0. So now again we simplify. 2x minus 4 minus y plus 1 plus z is equals to 0. 2x minus y plus z is equals to 4 minus 1. Or 2x minus y plus z is equals to 3. Done. Did you find something like this? Nice. You're doing fine so far.
Just a quick one.
Go ahead.
Where did we get this point 0, 2, -1 and 2, -1 and 1?
0,2. Oh, this one here.
Yeah, yes.
I extracted. I literally just changed the representation of that line. The line was presented in parametric form. I represented it in vector form. Remember, in vector form, a line like this with a point on the line x0, y0, z0, with parameter, let's say t, we'll have a, comma b, comma c. When presented in parametric form, it will be x is equals to x0 plus at. Y will be y0 plus bt. And z will be z0 plus ct. So I used that logic to reverse this. Do you get it now? Since there is no, there's only 2t here, meaning there's only this part, it means that x0 is 0. So here I have minus t, it means that the 2 is the y0. Here I have minus 1, it means that z0 is minus 1. The coefficient of the t is a here, it will be b here, it will be c here. So I have 2, negative 1, positive 1. Do you get it now?
Yes, sir. Thank you.
So let's look at that last one now. We're still trying to find the equation of a plane, but now the plane contains the line and it is parallel to that vector and this. Okay, what does that mean? So whatever the case, my attempt is always to just start. Things always work out as I go on. So let's see. Containing the line. So let's get this line. So they've given us a line in vector form. So from the top of your head, what do you think this line will help us with? Remember, to describe a plane, we need a point on the plane and a vector perpendicular to the plane. So without even thinking through so much, what are we going to extract from this line? What is it helpful with so far? Anyone? Well, we know to say when a line is given, this part of the line tells us a point on the line. Since the question is saying we are looking for a plane that contains the line, so it implies that this plane, if this is our plane, that line given lies on this plane. So the given line lies somewhere along this plane. Meaning a point on the line is a point on the plane. And since to describe a plane, one of the things we need is a point on the plane. We'll use the same point on the line that will be useful to us. So I hope you got that part. So that line they have mentioned there, let's assume that is this line. So a point on the line is a point on the plane. So a point on our plane we have obtained. It's 1, 2, 3. This will give us our x0, y0, and z0. Now, the next thing we need is the normal. Now we need a normal. So let's see what else the question says. So this plane contains the line. Other than containing the line, it is parallel to this vector and this vector. So these two vectors are parallel to this plane. And the second vector, okay, so if these two vectors are parallel to our plane, how do they look like? So it's like one vector is somewhere here, parallel, doesn't pass on our plane, maybe it passes on top of the plane. Doesn't necessarily have to lie on the plane. It can be above our plane, it can be below our plane. Can be even this one, we can argue to say that it is parallel to our plane. All we're saying is we have two planes or two lines which are parallel to our plane. Now, what does it mean? Or how are they then going to be useful? Well, it then follows that if we can find a vector that is perpendicular to one of these lines, since the two lines are both parallel to our plane, it means that they are also parallel to each other. No, let me not phrase it like that. They're not parallel, they are not necessarily parallel to each other. The plane is so wide and so on. So being parallel to the plane does not necessarily mean parallel to each other. So don't confuse that. What I mean here is that the two lines are parallel to our plane. One line is maybe like this, the other line might be like that. But if we use these two lines, if we get their cross product, what we get is going to be a vector perpendicular to both of them. So if we obtain the cross product of the two lines, the result is going to be a vector perpendicular to both vectors. Such a line perpendicular to both vectors, notice that now it becomes perpendicular to our plane. Again, see these, they are parallel to our plane, but a vector perpendicular to both, when extended, you should see that it will actually be perpendicular to our plane as well. That's the logic there. So since the two vectors have been given, did I copy them? Yes, I did. The two vectors have been given. All we need is to find a vector perpendicular to both. And that vector will give us our normal. To get a vector perpendicular to both, we just get the cross product. Again, order here will not matter. We'll use the determinant method to get the cross product. And here we've been doing this for some time, so you should know how it continues from here. So I have 3 and 2, that's 6, plus 1, minus j, and then I have 2 and 2, that's 4, and then 1 and 1, that's 1, then we'll get k. We'll have 2 and minus 1, that's minus 2, and then that'll be minus 3. So we have 7i minus 3j and minus 5k. So that becomes our normal. So we now have the two ingredients. The point is 1, 2, 3. Yes, that is 1, 2, 3. One, 2, 3. So we can now get our plane. So I hope at this point you now get how this goes. Is equals to 0. From the normal, we have 7 minus x0, which is 1. Remember, this is not a negative. B from the normal, minus 3, so negative here. From the point, we have 2. Then from the normal, we have minus 5. Then from the point, we have B. Then we simplify. 7x minus 7 minus 3y plus 6 minus 5z plus 15 is equals to 0. Now I have 7x minus 3y minus 5z will be equals to 7 minus 6 minus 15. And finally, our solution will be, this will be positive 1, then minus 14. Done. Is this what you got?